So welcome to the first afternoon session of this year's QIP. So just before we start, I think there's an announcement.
Yeah, so sorry to delay things a bit further. Some of you have already received an email and others have not. So there is a survey and it's actually quite important. You should fill it out and tell us what you think. You can find the survey by going to the QIP website and looking on the menu on the bottom left. There's a link to the survey. So the question is whether the number of talks at QIP should be increased, yes, no, and if it should be increased, how should this happen? So we want to discuss this in the business meeting to which you should all come, and to get some idea of what you all think, you should fill out the survey before. So the survey is open until 3 hours before the business meeting, so please fill it in. Thank you.
Okay, thanks very much. Okay, so we have two talks in the first part of this session this afternoon. The first of which is a quantum algorithm for computing the unit group of an arbitrary degree number field by Kirsten Eisentraeger, Hallgren, Alexei, Kitaev, and Fang. And Fang will give the talk. Okay, thanks.
Thank you, Ashley. And good afternoon, everyone. First, I want to thank the organizers and the program committee for giving us the opportunity to give this long talk. And I'm going to tell you efficient quantum algorithm for important number theory problem, which is considered hard classically. And this is joint work with Eisentraeger, Hallgren, and Kitaev. There are some technical issues with the resolution, and if you cannot see the text at the bottom, just let me know. I'll try to explain. Okay, so let me start with a very basic question. Which problems can be solved much faster on a quantum computer compared to classical algorithms? And you cannot see the text at the top. So let's be ambitious and ask for exponential quantum speedup. And number theory appears to be a good place to look for such examples. And in the breakthrough work by Peter Shor, he showed how to solve factoring and discrete logarithm efficiently on quantum computer. And this has tremendous impact on both quantum computing and cryptography. And later, Hallgren extended Shor's algorithm and solved the problem of computing the unit group in number fields, first in degree 2 fields and later in any constant degree number fields. And the similar techniques also gave efficient quantum algorithms for other problems in constant degree number fields. For example, finding a generator for a principal ideal and computing the structure of the class group. So don't worry if these terms like number fields don't quite make sense to you now. I'll explain in detail later in the talk. But what's important here is that while we can solve these problems efficiently on by quantum algorithms, the best classical algorithms are much slower. They typically take superpolynomial time. So in this work, we fully resolved the problem of finding the unit group in arbitrary degree number field. So as you can tell from the timeline, going from constant degree to arbitrary degree needs enormous effort. It took almost 10 years. And we feel lucky that we finally got a solution, and the solution is kind of neat in our opinion. So it turns out that all these quantum algorithms, including our new one, have a common structure. Basically, the number theory problems are reduced to a problem called the hidden subgroup problem, or HSP in short, which I'll define in a moment. So, namely, the input problem is transformed to a HSP instance on some group G, and then the efficient quantum algorithm is given to this HSP instance. Notice that in order to get an efficient algorithm for the original problem, both the reduction and the quantum HSP algorithm need to be efficient. So for example, the existing algorithms for finding units in constant degree number fields reduce the problem to an HSP instance on constant dimensional real space. And we can also solve this HSP instance efficiently. However, going to higher degrees, we encounter fundamental difficulties. So first of all, the reduction is no longer, where's the laser? Okay, so the reduction is no longer efficient because it takes time exponential in a degree. And moreover, the resulting HSP instance will be on high dimensional real space, and it is hard to solve by existing quantum algorithms. So we come up with new ideas to get around these difficulties. So first, we introduce a new definition for HSP on high-dimensional real spaces, and for which we can actually solve efficiently by a quantum algorithm. And then we show that arbitrary degree unit finding problem can be reduced to an HSP instance satisfying our new definition. One feature to notice here is that our reduction is quantum. Namely, the transformation is computed by a quantum algorithm. In contrast, previously, these reductions are typically classical. So in some sense, our quantum algorithm is taking advantage of the power of quantum computing in both steps of the algorithm. So this talk will be guided by the diagram at the bottom. So I'll first introduce our new continuous HSP definition, and then I'll explain some basics about number fields and tell you what the problem of unit finding is all about. And then I'll show you how our quantum reduction works and how to solve the HSP instance. Okay. But before doing that, I wanna spend a while to draw more attention from you, because I know it's hard to keep focused in a long talk, especially after lunch. And we know that Shor's quantum algorithm breaks many classical crypto systems. For example, the RC encryption scheme, which we use every day. And it may be less well known, but Hallgren's algorithm for degree 2 principal ideal problem breaks a key exchange protocol. So you may wonder, how about this new quantum algorithm? Well, our quantum algorithm seems relevant to attacking a branch of cryptography based on ideal lattices. But unfortunately, or maybe fortunately, currently no crypto system is broken entirely. So this is still an open question. So you don't need to know what ideal lattices are at this moment, but ideal lattices, they have received a lot of attention in recent years for at least two reasons. First, they are the central tool in quite few breakthrough results in the last few years in cryptography. For example, people are able to construct fully homomorphic encryption schemes based on ideal lattices. These are encryption schemes where you can directly do computation on the ciphertext without decrypting them. And you can use this to protect privacy of users against big clouds like Google or Amazon. And also, ideal lattices are used to construct code obfuscation schemes, which have many applications like software protection. So this is one reason. And ideal lattice-based crypto is interesting also because these ideal lattice problems, they are believed hard even against quantum algorithms. Actually, it is considered one of the promising directions in post-quantum cryptography, crypto systems that are supposed to be secure against quantum attacks. But is this indeed the case? Right now, the answer is I don't know. But our algorithm deals with similar objects, which are ideal lattices in high degree number fields. So at least it urges us to study more about these ideal lattice problems, either to break them or to gain more evidence about their hardness against quantum algorithms. So here I want to mention an approach of attacking ideal lattice-based crypto proposed by Dan Bernstein. So I want to say this is just an approach. It may or may not work, I'm not sure. But one key component in his approach is computing the unit group by some classical algorithm which takes time sub-exponential. And applying our quantum algorithm, this part immediately becomes polynomial time. Okay, so this is all I want to say about the connection to cryptography. So our algorithm solves an important problem in number theory. It also shows another example of quantum exponential speedup, and it seems to also have the potential to attack in classical crypto. All right, so in the rest of the talk, I walk you through our quantum algorithm, and let me start from our new definition for HSP. for the hidden subgroup problem. So what does HSP mean? Excuse me. So in the standard definition, there's a finite group G, and we're given a function f as our oracle, which maps the group G to some set S. And f is supposed to hide a subgroup H of G in the sense that, number one, it is constant within each coset of H, which we call periodic on H. And number two, it has distinct values on different cosets of H. Namely, it is injective on the quotient group G over H. And the goal here is to find the hidden subgroup H. So this definition extends to infinite groups like the integers and high-dimensional grids very easily. However, given a sensible definition for groups like the reals, turns out to be non-trivial. And at least one subtlety is about discretization. So you can still imagine a function f defined on the real line that is periodic with period r. And we want to access the function by computers in order to find the period r. However, computers, no matter classical or quantum, they are both digital. Namely, we can only evaluate the function on discrete grid. So we know the original function is periodic. So these blue dots, they are integer multiples of r. They all have the same value. However, the function after restricting to the discrete grid, it may lose the periodic property. As we can see from those red dots, which are roundings of the blue dots to their nearest grid points, they all have distinct values. So it becomes unclear whether we can extract information about the period from f delta. So to address this, previously, some extra condition was enforced on the function f delta. For example, you require periodicity is robust under rounding. And this definition works fine in low dimensions. However, it doesn't seem very nice in high dimensions. And in the very least, we don't know how to solve it efficiently, as I mentioned earlier. So we propose a new definition, and we can solve it efficiently. And there are a few distinct features of our new definition, and the keyword here is continuity. So again, we assume we have a function defined on R to the m, which is periodic over some subgroup H. And here we make the output of the function kind of spatial. They will be quantum states. And then next we weaken the injective property a little bit, which we call pseudo-injective. It roughly says that if two inputs, x and y, if they are far from being in the same coset, then their output states will be almost orthogonal. And most importantly, we require the function to be Lipschitz continuous. It roughly says, it intuitively says that if we shift the input by a little amount, then the output also just gets shifted by a small amount. And the goal here is still to find the hidden subgroup H. So these exact parameters and mathematical expressions are not important for this talk. It suffices to keep in mind these intuitive interpretations of our HSP conditions. All right. So let's look at a few interesting HSP instances that arise in solving those number theory problems. So we know discrete log reduces to HSP over the group Zn times Zn. The factoring reduces to HSP over the integers. And those constant degree number field problems, they reduce to HSP on constant dimensional real space. And in addition, fortunately, those HSP instances can all be solved efficiently. And in this work, we reduce the arbitrary degree unit finding problem to our new HSP definition on high dimensional real space where the dimension is proportional to the degree. And this instance can also be solved efficiently. So notice that all these groups involved so far, there are a billion. And non-abelian HSP is also very interesting. For example, if we can solve HSP on the symmetric group, then we get an efficient algorithm for the famous graph isomorphism problem. And also, the unit shortest vector problem, which is interesting in cryptography, it reduces to HSP on the dihedral group. But unfortunately, we don't know how to solve those non-abelian HSP instances. So this is in sharp contrast to the abelian case, where our work kind of completes the picture. Okay, so now let me introduce some number theory background in order to explain our quantum reduction. Okay, so what is a number field? So a number field is just a subset of complex numbers, and it is a finite field extension over the rationals. So for example, if we take an integer d, and we consider all numbers of the form a plus b squared d, where a, b are rationals, so this forms a quadratic field. And another interesting family of number fields is called the cyclotomic fields. Here we take a pth root of unity omega, and the field elements will be rational linear combinations of all of powers of omega. So inside the field, those elements which are also roots of monic irreducible polynomials with integer coefficients, they form a ring, which we call the ring of integers, and we denote it by O. And the invertible elements in the ring of integers form the unit group, and this is the object we want to find. And I'll denote the unit group by O star. So let me give you a couple of examples. So a trivial field is the rationals, and the ring of integers is just the ordinary integers. And here, plus minus 1 are the only units. And let's look at a more interesting example, the quadratic field. And for many d's, the ring of integers in the quadratic field will be of the form a plus b squared d, where a, b are integers. And in this case, the unit group will be generated by a single unit. For example, if we, probably this is hard to see in the back. So if we take d to be 109, then this special unit will look like this. You can verify it is indeed a unit. I mean, you don't need to see exactly what these are, but you can probably tell the unit has much more digits to write down compared to the input, which only has 3 digits. So this is indeed a non-trivial issue to properly represent the unit group, and I'll say more about this later. So next, we want to do computations in the number field, and in order to talk about the computational complexity, we use 2 parameters. The first one is the degree, n, which is the dimension of the field when we view it as a vector space over the rationals. And another parameter is the discriminant of the ring of integers. It roughly measures the size of the ring of integers. And I'll say more about this in a moment. So, for example, as the name suggests, a quadratic field has degree 2, and its discriminant is roughly d. And for the pth cyclotomic field, the degree is p minus 1, and the discriminant is pretty large. It's roughly p to the pth power. So we consider a computation efficient if it takes time polynomial in the degree and polynomial in the logarithm of the discriminant. So here's a summary of the complexity for computing excuse me, for computing the unit group we can see classical algorithms, they typically take time exponential in the degree and log discriminant. And previous quantum algorithms, they reduce the dependence on the log discriminant to polynomial, but they still take time exponential in the degree. And our work, which you cannot see, we give a fully polynomial time algorithm. You know, polynomial in both the degree and log discriminant. All right, now that we know some basics about the number theory and also our new HSP definition, let me tell you how to reduce the unit group problem to our HSP definition. Excuse me. So our reduction roughly, I mean, at a high level, it goes through 3 steps. First, we'll identify the unit group O star as a subgroup in a high-dimensional real space. And the main part will be define a function that hides the unit group and satisfy our HSP conditions. And in the end, we need to compute this function f efficiently by a quantum algorithm. And I'll skip this step in this talk. Okay, so we'll need to dig into a little we need to dig into the structure of the number field a little more in order to see how to set up the units as a subgroup. So it's known that we can represent a field element as an n-dimensional vector by under what so-called conjugate vector representation. And in this way, the ring of integers forms a lattice in R to the n. And this lattice will be very useful in the next few slides. So I'll denote it as O underline here. So I have been talking about the term lattices for quite a few times. So let me say a few words about it briefly, just in case this concept is not familiar to you. So a lattice is just a discrete subgroup of R to the n. So it is a integer linear combination of n linearly independent vectors. And we call these n vectors a basis for the lattice. So for example, here, if you take these 2 vectors, and they will generate a 2-dimensional lattice, those little dots. And one fact worth mentioning is that a lattice has many, like infinitely many bases. For example, these 2 blue vectors, they also form a valid basis for this lattice. And sometimes we're interested in the determinant of the lattice, which is basically the volume of the fundamental domain. And this is pretty much what we need to know about lattices in this talk. And now I can also tell you how the discriminant is defined. It's just the determinant of this lattice O underline squared. Okay, now back to units, the invertible elements in the ring of integers. So it's often convenient to write the units in the so-called log coordinates. Basically, we take the logarithm of each coordinate in their conjugate vector representation, which I denote by ui. And there's another characteristic for units, namely they have algebraic norm 1, which says that the product of those coordinates will be 1. So under this additive structure, we know that the summation of the coordinates, of the log coordinates, will be 0. So therefore, there's one redundant coordinate. So we can place the unit group as a subgroup in R to the n minus 1. Namely, the unit group lies in a hyperplane in a n-dimensional real space with the constraint that the summation of the coordinates equals 0. And I want to point out that, well, this is this is invisible, and which indicates it's not very important. So here I'm being oversimplifying, because at least you can see when we take the logarithm of the absolute value, at least the sign information is missing. So the actual group structure is more complicated, which I'm not going to go into, but the description here is good enough for this talk. Okay, now let's see how to define a function that hides the unit group. So our function, our HSP function, will be a composition of two functions. The first one, which takes an input vector and produces a lattice in R to the n. And then for technical reasons, we introduce the second function, which encodes a lattice into some quantum state. So let me explain the classical function, the first part first. Okay, so let x be an input vector with the constraint that the summation of the coordinates equals 0. And then under the function f sub c, it will output a lattice, which is a transformed version of O underline. So let me tell you what the transformed lattice looks like by example. So let's look at the quadratic field, the real quadratic field. And here the degree is 2, and O underline is just a 2-dimensional lattice. And then given an input vector which looks like x minus x, for any lattice point in the original lattice, it will be shifted to a new point under FC. Specifically, the new point will be coordinates-wise multiplication between e to the x and v. So in this case, we can see it's basically stretching along one direction and squeezing along the other. And we can also observe that the mapping FC preserves the algebraic norm. As we can see here, the product of the coordinates, they remain the same. So here's the animation for the real quadratic example. As we can see, the lattice points, they all move along these norm lines. Okay, so hopefully you get the basic idea of the function FC. And actually it already has very nice properties. And first, it's periodic over the unit group. And this comes from the fact that if we transform O underline by a unit, we still get O underline. So if an input vector corresponds to a unit, then the output lattice on x plus y will be the same as the output lattice on x. And we can also argue the function is Lipschitz, because intuitively, if you shift the input by a little bit, the resulting lattice will be quite similar to the original one. It's only just a small shift. On the other hand, if two inputs differ by a lot, then the function, the lattices they generate will be quite different, and this is essentially what pseudo-injective asks for. So this basically finishes the description for the first part of our HSP function. So we still need to compute the function FC efficiently. I'm not gonna explain this in a talk, but I want to point out that this is quite tricky. For starters, we can see that e to the x will be doubly exponentially large, so we cannot afford doing the multiplication naively. And to make things worse, since we are dealing with rational approximations to real numbers, we need to carefully control the precision loss in any step of the computation. Okay, so we've seen a function FC which already satisfies some nice properties. So you may wonder what's still missing. Well, I have been vague about how to represent the output of the function fc, which are supposed to be lattices. So a natural choice will be, outputting a basis for the lattice. However, there's no canonical basis for real-valued lattices. In particular, even if two inputs generate the same lattice, the output basis from fc might be completely different. So we're missing a unique representation for the outputs of fc, and this is needed in the quantum HSP algorithm. So in order to fix this, we introduce the second part of the function. We encode the lattice into a quantum state, which looks like this. So it takes we take a superposition over all lattice points under a wide Gaussian envelope. So this roughly tells us the overall structure of the lattice. So I want to mention that this Gaussian should have a large parameter S, because otherwise it seems hard to create such a superposition. And then for each lattice point, we encode it into a quantum state using what we call a Strano encoding. And the goal here is to make sure that the encodings of two vectors will be kind of close, only if the two vectors are nearby in a space. And it's easy to see that the naive approach, by truncating a real number and representing them in the computational basis, this doesn't work. So I claim that composing FQ with FC will give what we want. In order to see that, I want to spend a while to explain the Strano encoding. So this is a little gadget which I think could be useful elsewhere. So let me start from encoding a real number. So suppose we have a real number v, and we pick a grid of size delta, and suppose we fall between the kth and k plus 1th grid points, and we encode this information by taking superposition over k and k plus 1. And then for the finer position, namely the distance to the left end point, we encode that into the amplitudes. So it's going to take a higher amplitude on k if it's closer to the kth grid point. So we can observe that if another point v prime is close to v, then their Strano encodings will have a large inner product. And as v prime moves away from v, their inner product will decrease. And finally, if v and v prime are 2 delta away, then their Strano encodings will be totally orthogonal. And these properties will be useful in just a minute. So once we can encode a real number, we can also encode a high-dimensional vector, just coordinate by coordinate using the same technique. So here's another animation showing the Strano encoding. Okay, that's about enough. Okay, so recall our quantum encoding for a lattice takes a superposition over all lattice points, and for each lattice point we encode it into by the Strano encoding. So if you look at the inner product between the quantum encoding of two lattices, L and L prime, we can find that only if 2 points are close by, they contribute to the inner product. Because if 2 points are far apart, then their Strano encodings will be orthogonal. So we can conclude that if two lattices are kind of similar, namely we can approximately pair up the points between these two lattices, then their quantum encodings will have a large inner product. On the other hand, if two lattices only have a small overlap, their the inner product will become very small. So now we can obtain our HSP function. So a claim that FQ composing FC will be periodic over the unit group, and it satisfies our HSP conditions. And by invoking our quantum HSP algorithm, which I'll describe next, we can compute the unit group efficiently. So, but before doing that, I want to make a final remark. So this function FC may be very specific to the structure of the number field, but the quantum encoding function FQ, and in particular the Strano encoding for real value vectors, they could be of independent interest. We've seen that FQ gives us a canonical representation for real value lattices. And actually, you can also use the Strano encoding to reduce all existing abelian HSP to our HSP on R to the M. So they can be solved under a unified framework. So I expect more applications of the quantum Strano encoding. Okay, so in the last few minutes, let me tell you how our quantum algorithm works. Sorry, how the quantum HSP algorithm works. So suppose we are given an we are given an oracle function f that hides a hidden subgroup. And although the whole point of this work is about high dimensions, but I can only give examples in low dimensions. So let me draw a periodic function on the real line, which I call the real domain. Okay, so by Fourier analysis, we know that in the Fourier domain, we get a spectrum that's peaked at the dual group. For example, in this case, we'll get multiples of 1 over R. So imagine if somehow we can sample from this spectrum, then it's conceivable that we can recover the dual group and also the original hidden subgroup. But unfortunately, we cannot compute the continuous Fourier transform on a computer, which is digital and only has finite memory. So in reality, we need to truncate and discretize the function. Namely, we're going to evaluate f on a bunch of discrete points inside a finite region. And the goal here is to approximate the ideal Fourier spectrum. So the question is what to do and what we get in order to recover the hidden subgroup. So to figure this out, let's look at how truncation and discretization affect the ideal spectrum. So first, truncation, which is we multiply the function by some window function W. And by the multiplication and convolution duality, we know that the Fourier transform of the product of two functions will be the convolution of the Fourier transform of each individual function. And since the window function, its Fourier transform looks like this, so we get a spectrum. We get a spectrum that looks like this picture. So this picture kind of tells us that the samples we get here will still be nearby the ideal samples. Again, this is oversimplifying. In fact, we will need some smooth window function. We need to carefully pick this window function. And fortunately, there exists such nice window functions, so we are still good. Now, how about discretization? In formal language, we restrict f on discrete grid delta z. Namely, we get a function f delta which respects the original function f on those grid points, but is undefined elsewhere. So by the Poisson summation formula, you can see that this causes the Fourier spectrum to wrap around a region of size 1 over delta. So namely, the new amplitude at a point z will be the summation of all old amplitudes of the points which equals the modulo 1 over delta. So you can imagine in general, this could totally mess up the Fourier spectrum due to some bad cancellation. But fortunately, we have the Lipschitz property. It saves us. a Lipschitz function will have a small tail in the Fourier domain. As you can see in this example, let's consider the constant function, which is perfectly Lipschitz. And its Fourier transform in the Fourier domain, it's perfectly concentrated at the origin. So this is just an extreme example, but you can try a couple more to convince yourself. So as a result, because of this small tail, we can pick a fine enough grid so that wrapping only causes a small disturbance in the Fourier domain. So the Fourier spectrum is pretty much preserved. So to summarize, if we pick a nice window function and also a fine grid for discretization, then we get a spectrum that approximates the ideal spectrum pretty well. And this spectrum can actually be obtained by applying the Fourier transform over the integers on this truncated and discretized function. And this is basically what our algorithm does using a technique called phase estimation. So the details about phase estimation are not important here. The whole point is we can sample from this spectrum and hence recover the hidden subgroup. So I want to point out that in our algorithm, we treat this function after truncation and discretization as a function defined over the whole integers. Namely, we view it as an infinite sequence, even if it's 0 outside the window. In contrast, previously, this function, maybe this is hard to see, this function after truncation and discretization are usually considered a function over a finite group, and then quantum Fourier transform is applied, which performs the discrete Fourier transform on a finite group. And it is hard to analyze the resulting Fourier spectrum directly. And existing analysis only shows that we can get a clean sample with probability 1/2 to the m. And this obviously fails in high dimensions. So our analysis stays in the continuous world as much as possible. Namely, we analyze what happens in the ideal world, which is much easier to analyze, and then it suffices to show that we can approximate the ideal world good enough. Okay, so here's the outline of the algorithm, of our algorithm. This is just basically rephrasing the pictures in the last few slides. I just want to show you the main difference between our algorithm and the previous algorithms, and also give you a sense that the intuitive description in the last few slides can indeed be turned into a formal analysis, although it takes quite some work. Okay, let me ramp up. So we've seen a quantum reduction from arbitrary degree unit finding problem to HSP instance that satisfies our new definition, and we can also solve this new this HSP instance efficiently. So hopefully I managed to deliver the main ideas of the whole algorithm. So our result suggests a few interesting future directions. So the natural one is to solve other problems in number fields and its extension to function fields. And more generally, we can explore what else can be solved in this new continuous HSP framework. Of particular interest, can we solve some idealized problems and break some crypto system based on them. So finally, I want to update that in a recent work with another postdoc at LQC, we extended the work that I presented here, and we solved the principal ideal problem and class group in arbitrary degree number fields. Okay, I'll stop here, and I'm happy to take any questions from you. Thank you.
Indeed, are there any questions? Okay,
So I lost everybody.
No. So I do have one question about another another future direction, which is to do with the parentheses in one of these things. So do you think your results say anything, or might have any potential scope to say anything about continuous non-abelian hidden subgroup?
Non-abelian. That's a good question. Actually, that's one question I want to ask you in the morning during your talk. And honestly, I don't know. I don't know the answer. Seems like the techniques are not very applicable in non-abelian HSP cases. So I guess that's the best I can say.
Okay, cool. Thank you. Any other questions? Oh.
I was just wondering what, if you have any examples of other problems that you said, other problems in number fields? The first point you said is other problems in number fields. I was just wondering if there are...
Oh, sure. Like, if you open a book like algorithmic algebraic number theory, you can find tons of problems. So the unigroup and principal ideal problem and the class group problem, these are the, I don't know, the most theory problem that people study. And there are absolutely others, like solving norm equations, and I don't know. There are tons of them. So and you are welcome to work on any of them.
Okay, we have a question over here.
Yeah. Do you have a formal description of how sensitive your Fourier transforms and convolutions are to changes and error rates and things like that?
The sensitivity. What kind of error are you considering?
Well, in particular, the case where you go over an edge and you get a relatively sudden change in the value of one of these discrete transforms. You do call out that you're not going to allow that in practical problems. But what is the sensitivity when you do encounter those kind of functions?
Well, in general, it's hard to tell. Like, there are bad examples, and here we are just identify one scenario where these errors are like under control.
Yeah.
So this is just one positive example. And there are negative examples. But I mean, really, this should be like case by case, I think.
Okay, thank you.
Okay, maybe one more question.
How this new algorithm is compared to the previous algorithms for constant degree extensions? So, I mean, what's the ingredient that you can use for arbitrary degree extensions?
So there are two steps in both the old function, old algorithm and our new algorithm, and the two steps are both different in our new algorithm. And I think I would say one key ingredient is the Lipschitz condition. So in some sense, our HSP definition is kind of stronger than the previous HSP definition. So the functions satisfy nicer properties, so that it's easier to see what happens when you do those Fourier transform. So.
Okay, great. So shall we thank Fang again?